Now, the example I gave in step 2 was pretty simple. It just had a single term in s plus 3, a single root of s in the denominator. But if you've got a more complicated problem, it requires more work to solve. If we can't directly find the solution by step 2, we're going to have to find all of the poles. And the poles are a fancy word for the roots of the denominator. And you can do that by either factoring, by hand, or if it looks like you can't factor it, use the quadratic formula. Where you'll remember the quadratic formula is minus b plus or minus the square root of b squared minus 4ac all over 2a. So let me give a quick example of this. Let's say we have s squared plus 4s all over s plus 2 times s squared plus 4s plus 3. Okay. You can hand factor the bottom. This part factors into an s plus 1 root, and I'll write the original s plus 2 next, just because it's in order, and s plus 3. And so now we look, because we've factored this as shown here, now we can write down our poles are at s equals -1, -2, and -3. Now at this point, it's a good idea to do a quick check. The real part of all your poles should always be negative, or possibly 0. They should never be positive. Now, there's 4 choices for your poles. The poles may be unique, like they are here. In other words, for an even simpler case, 1 over s plus 2, s plus 3 yields poles of s equals -2 and -3. So they could be unique. They could be repeated. If we had something like 1 over s plus 2 squared, that would give us poles of s equals -2 and -2. And these are all example of real valued poles. But besides being real valued poles, you know that if you apply the quadratic formula, you might end up with complex valued poles. And if 1 is a complex number, its complex conjugate will also appear. So as an example of that, let's say you've got 1 over s squared minus 4s plus 13. That you'll put into the quadratic formula, yielding poles of -2 plus or minus j3. So just as a quick check, notice that the real part of your pole is again negative, as they all should be, negative or 0, and that the imaginary part appears in complex conjugates. Now, the other type of pole you could have is if you square this term. And now, of course, you'll have repeated complex conjugates. S will be equal to -2 plus or minus j3, and also -2 plus or minus j3. Now, of these 4 possibilities, I'm going to talk about how to do this top left group of 3. I'm not going to talk about how to do this bottom right set, my entire life as a practicing engineer in industry and in graduate school, and having taken multiple sets of courses all the way through and including a doctorate, I have never encountered in either actual practice or even theoretic work this bottom right case. If you're curious how to do it, it's in the text. But I'm going to focus on how to solve problems with real and unique poles, real and repeated poles, and also complex conjugate poles.